If no question, we'll go to the next section, the Riemann zeta function. The discussion in your textbook is quite long. It's mostly mathematical, and basically is to extend the domain of the zeta function, because at first it's defined with some restriction on the argument, but it actually, the whole function actually defined over the whole complex plane. But in order to do that, in order to do some so-called analytic continuation, we need to, there's some discussion and to derive the alternate form of the function other than the original definition. So that's why it took us so long, such a long discussion. We probably won't go through all of them. And there's something very interesting, is especially the last part, that there's infinite product expression. That's, I think, is also due to Euler. Right? That is very interesting, actually. So we might talk a little bit about that. Let's see. We see how much we can go now, because all this complex variable discussion to generalize or to do the analytic continuation can be quite tedious. But anyway, we'll see. So the original definition is quite simple. So this zeta function depends on z. Originally, you defined it as a real number and likely a positive number. Actually, there's a restriction based on the form. See, it defined as sum of n of 1 to infinity n to the minus z vector. And obviously, if z equals to 1, is the harmonic series, which is divergent. So, and then just a little bit consideration will show that the convergence requires z greater than -1. So required. Let's see what your text will talk. I think that is true. Maybe we define this as just a real number, then requires z greater than 1. Right? So that's the original definition, and then you can extend to complex z also, but I think the consideration also, the real part of z is greater than -1. So over the whole complex plane, now you define over z plane as 1 is of -. Actually, this was later on. There's another value that is very important. 1. What is 1/2 real? This is real z. Imagine z. Right. Now, for using this formula, you can define the zeta function over here. Okay, or the large z, which is a simple formula. You can define it. Right. And now there are ways to extend that. The text will actually discuss that somewhat later in equation 13.68, but we could do that now. There's another topic in chapter 12 is the Dirichlet series, and there's another form. This is one Dirichlet series, but the convergency of this function is, I mean, you can improve the convergency by doing a trick like that. You define another series, because this series has a coefficient all positive, right? This is not an alternate sign series. All terms are of the same sign, all terms are positive. So you can increase the convergency by changing it to an alternate series. Okay, so that just take a little bit of consideration, and the idea is that so it's easier to write it out explicitly rather than doing abstract. You see, you just write it like this is 1 to the minus z, right? Now this discuss, see how much time I have. Yeah, 20 minutes about. And just write out explicitly, and like the first term is 1 over 1 to the z, right? And then the second one is 1 over 2 to the z, then 1 over z to the z, and so on. Oh, I should add a little bit more. Right, and we want to get the alternate series. I think we did something like that in when we talk about an example in Fourier series chapter, but let's repeat that maybe. So this is this function, right? And what we want is multiplied by I think is multiplied by 2 times 2 to the minus z. Okay. Because we want to make it alternate. If you multiply by z2, so this is zeta z. We multiply by 2 times 2 to the minus, or 2 times 2 divided by 2 to the z. We will do that. Right? The trick is we multiply 2 to the z. We move this first term to the second slot instead of the first one, right? And then that would be 2. And then this is 1 times 2 is 2 to the z, right? And then the second one, we move it to the fourth slot. So this is, right? This is plus, because 2 to the z times 2 to the z is 4 to the z, right? And so on. You get, so 3 will go to the 6th one, right? And there's a factor of 2 also. Right? Okay. And the idea is that we subtract this from this one, to subtract this. And then we get, so this becomes 1 minus 2 to the 1 minus z, right? Multiplied by zeta z. Now equals to 1 over 1 z. And now this subtraction, because of this factor of 2, basically flipping the sign of this term, minus 1 over 2. And keep this 1 over 3 to the z. And now this one is minus 1 over 4 to the z. Right? Can you see that? So every time you subtract that, you flip this all this with n is even. All these terms are sign flip. Okay, so this is what we call the A to Z, defined as A to Z, which is, if you write it like this one will be, we have 1 to infinity minus 1 to the n plus 1, n plus, I mean, basically even n will be negative, odd n will be positive, and then the same n to the minus z. Right? And then so by this equation, you can define zeta z equals to 1 over 1 minus z. And then this summation. And this trick is useful in the sense that you change the series from same sign series to alternate sign series, right? And you remember the convergence of alternate sign series is not restricted. Now you only require the terms go to 0 I think it's called the Nipnik criteria or something like that. Right. So this one only require the term goes to 0 as for a large n, right? That basically required only z greater than 0. And the other factor is analytic. As long as there's no pole, there's a one pole, and this turns out to be the only pole of the Riemann Zeta series is when z equals to 1. Z is equal to exactly real number 1, right? Because 1 minus 1 is 0, 2 to 0 is 1, 1 minus 1 is 0, so the denominator is 0. Okay, so only there's a pole, there's actually a pole here. That's the pole of the Riemann Zeta function. Other than that, the whole complex spring, the Riemann Zeta function is analytic. Okay, so that one property of the Riemann Zeta function, there's only one pole. Okay, but then now because of this, using this definition, you actually extend the domain. Instead of the greater than 1, you actually extend it all the way now, including all the way to 0, to the right of 0, real 0. So you can get all zeta function defined for all real z greater than 0. All right, so that's one trick.